Let's look at some more problems where we are solving trigonometric equations. Now, take a quick look at the directions here, and you might notice that they are slightly different. Rather than just solve, this says find all the solutions of the equation in the interval 0 to 2 pi. All right, so in this particular case, we are not going to have an infinite number of answers like we had before. We are going to instead have a finite number of answers, and all of our answers are going to be on the interval 0 to 2 pi. Notice that we have a bracket on the outside of this 0, meaning 0 could potentially be a solution, and we have a parentheses on the outside of the 2 pi, meaning that the 2 pi is not included in our solution set. So let's see if we can't get this one started. The good news is that we only are dealing with one type of trig function, sine x's. So we don't have to worry about using any fundamental identities to try to rewrite the expression. However, we do need to recognize that this is actually written in the form of a quadratic. Notice our related algebraic equation, 2x squared minus 7x plus 3. These two equations are similar, except instead of x's, here I have sine x's. Well, how do we solve quadratic equations? We solve them by setting the equation equal to 0 and factoring. Quadratics are always going to factor into a binomial times a binomial. In this case, our quadratic factors into 2x minus 1 times x minus 3 is equal to 0. This means that our trigonometric equation over here is going to factor in the same manner. Instead of 2x minus 1 times x minus 3, I get 2 sine x minus 1 times sine x minus 3. So we just replace all those x's with sine x's. Now that we have factored our equation, we want to set each of the factors equal to 0. Again, the zero product property says if either one of these quantities equals 0, the equation will be true. That means when sine of x is equal to 1/2, our equation will be true, and when sine of x is equal to 3. Notice we set each of the factors equal to 0, and we solve for the sine of x. Now that we have isolated our trig function, we can go to our unit circle. Let's identify the location of the angles that have a sine value of 1/2. Well, sine corresponds to the y-coordinate. That's going to be here at pi over 6, and here at 5 pi over 6. Notice that there are no solutions for values or angles that have a sine of 3. Remember, our unit circle, the maximum y value is 1. We cannot get an output of 3 from sine. That also relates to the range of our sine graph. Okay, so that's not going to give us any solutions. Well, those are my only two answers on the interval 0 to 2 pi. Because we're not trying to find a general solution here, I only want the answers that are in this particular region right on the unit circle. X equals pi over 6 and x equals 5 pi over 6 are my only answers. Again, sine of x equals 3. That's not going to give us any additional solutions. Let's look at another one here. We now have secant x plus tangent x is equal to 1. Secant x plus tangent x is equal to 1. So this one's tricky. We've got two separate trig functions, secant x plus tangent x. And we can't write secant in terms of a tangent, and I can't write tangent in terms of a secant. There's no way to change these to rewrite it in terms of a single trig function. So, and there's no common factor either that we can factor out. If that's the case, this might be a scenario where we want to square both sides. You might recall from earlier on, one of our pro tips, we said, number 5 here, if it is not possible to rewrite an equation in terms of a single trig function, it may be possible to square both sides of the equation to allow the use of Pythagorean identities. All right, so let's see if we can't do that and get the problem to work out for us. All right, so here we are again. Secant x plus tangent x is equal to 1. Let's square both sides of the equation. Well, secant x plus tangent x quantity squared, That actually means secant x plus tangent x times secant x plus tangent x. And 1 squared is just equal to 1. Let's now do out our algebra. We have two binomials. If we're going to multiply these together, we must FOIL, or use the distributive property of multiplication. Secant x times secant x, that will give me a secant squared x. Notice my outer and inner terms. I have a secant x tangent x plus a secant x tangent x. That gives me 2 secant x tangent x. And my last terms, tangent x times tangent x, gives me tangent squared x. Secant squared x plus 2 secant x tangent x plus tangent squared x is equal to 1. Okay, so we still have two different types of trig functions, right? But maybe we can begin to rewrite in terms of a single trig function. Well, if we had to choose between secants and tangents, I'd say tangents are probably a little bit easier to work with. So is it possible to rewrite secant squared x in terms of a tangent? Well, think to our Pythagorean identities. We had the Pythagorean identity 1 plus tangent squared x is equal to secant squared x. That means I can replace this secant squared x with a 1 plus tangent squared x. All right, so I now have, notice that's this grouping right here, 1 plus tangent squared x plus 2 secant x tangent x plus tangent squared x is equal to 1. Here, if I now subtract 1 from both sides of the equation, this one is going to subtract with that one. And if I combine my like terms, I've got a tangent squared x plus a tangent squared x. That leaves me with 2 tangent squared x plus 2 secant x tangent x is equal to 0. All right, at this point, we can recognize that we have a greatest common factor between our two terms. Our greatest common factor is going to be a 2 tangent x. And good news is, this is already set equal to 0, so let's go ahead and factor out our greatest common factor. 2 tangent x times tangent x plus secant x is equal to 0. And as we have done with all of our factors, after we factor, we use the zero product property and set each one of our factors equal to 0. First one, setting it equal to 0, will give me tangent x is equal to 0. And my next factor, tangent x plus secant x is equal to 0. Notice this 2, if I divide both sides of the equation by 2, the 2 goes away. All right, so I have tangent x equals 0 and tangent x plus secant x equals 0. This one's good to go to the unit circle. However, tangent x plus secant x, it's going to require a bit more manipulation. Okay, well, we still have two different trig functions. Let's see if we can combine them somehow. We can recognize that tangent and secant can both be written in terms of sines and cosines. Tangent x is the same as sine x divided by cosine x, and secant x is 1 over cosine x, which conveniently creates a common denominator. Because we have a common denominator, we can combine those two fractions, leaving us with sine x plus 1 divided by cosine x is equal to 0. And one thing to make note of is that the only time a fraction will ever equal 0 is if the numerator is equal to 0. Now, that is true if the denominator is not also equal to 0, but setting the numerator equal to 0 will give us a start. Sine of x plus 1 is equal to 0, which means sine of x is equal to -1. Okay, all right, a lot of manipulation there. So we've got tangent x equals 0, sine x is equal to -1. We have isolated our trig functions, and now we can go to our unit circle. Let's find the angles that have a tangent value of 0. Now again, read the directions carefully so you know how to answer the question. This is only looking for solutions between 0 and 2 pi. Well, what are the angles? 0 is going to be one of our solutions. What else has a tangent of 0? Pi. And, well, 2 pi does as well. However, again, recognize we've got a parentheses on the outside of 2 pi, so 2 pi will not be included in our solution set. All right, what angle has a sine value of -1? Well, that would be 3 pi over 2. So we have these three angles. X is equal to 0, pi, and x is equal to 3 pi over 2. We're not done yet. Because we squared both sides of the equation, we must check for extraneous solutions. Those are solutions to the equation that we ended with that are not solutions to our original equation. So what we want to do is we want to substitute all of these answers into our original equation to check and make sure that they work. Starting with 0. If I plug in 0, the secant of 0 plus the tangent of 0 is equal to 1. Well, the secant of 0, secant is 1 over cosine, so this is 1 over the cosine of 0, gives me 1, plus the tangent of 0 is 0. 1 plus 0 equals 1. Yes, that solution checks out. Let's test pi. The secant of pi plus the tangent of pi is equal to 1. Well, the secant of pi, that's 1 over the x-coordinate, that's 1 over negative 1 is a negative 1, plus the tangent of pi, that's 0, negative 1 plus 0. That does not equal 1. Pi is an extraneous solution. And we can test 3 pi over 2. The secant of 3 pi over 2. Well, again, secant 1 over the x-coordinate. The x-coordinate of 3 pi over 2 is 0. 1 over 0, undefined. Therefore, 3 pi over 2 is also going to be an extraneous solution. So our only answer in this case, x is equal to 0. All right, now you might have even noticed that back when we were doing this manipulation here, notice sine of x was equal to negative 1, and we got x was equal to 3 pi over 2. Notice that if you were to plug in 3 pi over 2 into the denominator, we would actually get an undefined value. So that tells us that x equals 3 pi over 2 is also not a solution. You could have picked up on that here in this step, or picked up on it as you were checking for your extraneous solutions in the end, right? Either way, we are able to verify x equals 0, our only solution. So that's finding solutions to equations in the interval 0 to 2 pi.